So far, when talking about colligative properties, we're focused on solutions where the solutes are non-volatile. Okay, so what we're going to do now is we're going to look at solutions where the solutes are volatile. And again, what did we say a volatile solute is? Something that's volatile is something that ordinarily exists as liquids or gases in pure form. Okay, the non-volatile solids would ordinarily be solids under ordinary conditions. Now, for example, let's take a look at a mixture of two liquids. We can define what's called an ideal liquid mixture as one where both components of your mixture obey Raoult's law. If you remember what was Raoult's law, if A is a component of my mixture, like my solvent, okay, the partial pressure or the vapor pressure of A, that would be in equilibrium with my mixture. So if I have liquid right here, a mixture of A and B, okay, in the gas, I also have A and B since A and B are both volatile, right? So the partial pressure of A in the gas would be equal to its partial pressure if it were pure multiplied by its mole fraction in the liquid phase. So this is Raoult's law, remember? So Dalton's law of partial pressure says that the total pressure of your gas mixture is just the sum of the partial pressures of the components. So the total pressure above your liquid, that will be in equilibrium with your liquid, is just the sum of the partial pressure of A plus the partial pressure of B. So you can see P star B times X of B, that's the partial pressure of B. And P star A times mole fraction of A is the partial pressure of A. Okay? So that's what we would expect if we have what's called an ideal solution, where ideal mixture of two liquids where both components of your mixture obey the Raoult's law. Okay. So most components, in fact, do deviate from Raoult's law when their mole fraction is significantly less than 1. In those cases, we say they typically obey what's called Henry's law. But let's look at Raoult's law first. Let's look at the consequences of Raoult's law if both components of your mixture obey Raoult's law. Okay? So let's look at this question right here. At a given temperature, pure liquid A has a vapor pressure of 80 torr. What does that mean? That means P star A is equal to 80 torr. Okay. And pure liquid B has a vapor pressure of 100 torr. So that means P star B, the vapor pressure of pure B, would be 100 torr. Now, let's say you were to mix 0.2 moles of liquid B with 0.8 moles of liquid A. Okay? So you have a liquid that has 0.2 moles of liquid B and 0.8 moles of liquid A. What would be the vapor pressure of the resulting solution? Let's see. The vapor pressure would just be equal to PA plus PB, right? Partial pressure of A plus partial pressure of B. So it's going to be P star A times mole fraction of A plus P star B times mole fraction of B. Okay, that's the mole fraction of A and B in this case. So this is going to be P star A is what? 80 torr times mole fraction of A plus P star B, which is 100 torr, times mole fraction of B. How do we solve for the mole fractions? Formula for mole fraction? Mole fraction of A is moles of A over total moles. How many moles of A do we have? 0.2. And our total would be, oops, nice. Moles of A is 0.8, sorry. And that's our total moles. That's 0.8 plus 0.2. 1. So mole fraction of A is just 0.80. What would be the mole fraction of B? 1 minus 0.8, or you can say moles of B over total moles, which is 1.00, is going to be 0.20. So let's plug those numbers in. Mole fraction of A is 0.8. And mole fraction of B is 0.20. Okay. So you can see that the vapor pressure of A is lowered, right, to 80% of what it was. The vapor pressure of B is also lowered to only 20% of what it would be if it was pure. And so what's the total pressure here? Go ahead and calculate that, and I'll collect the answers A, B, and C. Is it between 80 and 100 torr? Greater than 100, or is it less than 80? Ready? Or do you need time? No? Need one more clicker. Okay. Answer is between 80 and 100. Okay? In fact, if you were to make a plot of this, it's a way to visualize this. If you were to plot, okay, versus mole fraction, okay, mole fraction of A from 0 to 1, okay, what would be the vapor pressure of A? And let me put that in red. Versus mole fraction of A. P sub A is equal to P sub A star times XA, right? So when mole fraction of A is 0, what's the partial pressure of A? It's gonna be 0, right? If XA is 1, what would be the partial pressure of A? It's PA star, right? And what is PA star? That was 80 torr, right? This is PA star. This is 80 torr. And so if you were to plot that, this is what you get. You just get a straight line, okay, for that. What would happen if we were to plot partial pressure of B versus mole fraction of A? What did we say partial pressure of B was? P star B times XB, right? Which is P star B times 1 minus XA. Remember, XB is 1 minus XA. Mole fractions add up to 1. So that's equal to P star B minus P star B XA. Okay. So when XA is 1, when XA is 0, if this is 0, what is my partial pressure of B? It's just P star B, right? And what is P star B? It's 100. So when XA is 0, it's going to be 100. That's P star, that's PB. And when it's pure A, when XA is 1, what is P star B minus P star B? It's going to be 0, right? So if you were to plot the partial pressure of B versus mole fraction of A, it's going to look like this. It's going to be a straight line. So if you add these two up, okay, what you'll get, so if you add the black and the red, what you'll find is you just get this straight line right here. So a mixture of the two will have a vapor pressure that's in between. Okay, so that would be the consequence of both liquids following Raoult's law. Now, they're not necessarily going to follow Raoult's law. Like I said, there tends to be deviations from Raoult's law. We're not going to get into that. This would be the ideal case. All right. How about this one? At a given temperature, pure liquid A has a vapor pressure of 80 torr, while pure liquid B has a vapor pressure of 100 torr. Same example as before. In a liquid of mixture of A and B, the mole fraction of B is 0.2. What would be the mole fraction of B in the vapor? In the liquid, it's 20% B. In the vapor, is it still going to be 20% B, less than 20% B, or is it going to be larger than 20% B? Let's try to use some common sense here. Which one's more volatile, A or B? Vapor pressure of A is 80 torr. Vapor pressure of B is 100 torr. Which one is more volatile? More volatile has a greater tendency to be in the gas. So, vapor pressure gives you an indication of volatility, right? The higher the vapor pressure, the more volatile. So we say B is more volatile, right? So if it's only 20% B in the liquid, in the gas, you would expect more than 20% B. Okay? So it's going to be larger than 0.2. Let's actually calculate that. Okay? P sub A is how much? It is P star A times mole fraction of A. And what's P star A? 80. What's the mole fraction of A? It's 0.2, right? No, that's B, so that's 0.8. What is 80 times 0.8? 8 times 8 is 64, so 64.0 torr. What is the partial pressure of B in the vapor? P star B times mole fraction of B. What's P star B? 100 torr. What's the mole fraction of B? 0.2. What's 100 times 0.2? 20 torr. Okay. How do we get the mole fraction of B in the vapor? Mole fraction of, so we don't confuse it with the mole fractions in the liquid. We're going to use a different letter. Okay, we're going to use Y for mole fraction of B in the vapor. So Y sub B is mole fraction of B in the vapor. Okay. And if you remember your earlier class, Chem 105, what would this be? This is just going to be partial pressure of B over the total pressure, right? So that's going to be equal to 64.0 over 64.0 plus 20.0. P total is just PA plus PB. Okay. So this will be 64.0 over 94.0. What's 64 over 94? Not 94, 84. 64 divided by 84, it's 0.76. Oh, I'm sorry, it's not 64. Partial pressure of B is 20. Sorry about that. This is 20.0. Okay. So this is 20.0 over 84.0. You can see that is, oops, 20 divided by 84. Small fraction is 0.238. Okay? That's as expected. We expect our vapor to be richer in the more volatile component compared to the liquid. All right. So that's Raoult's law. Like I said, solutions do tend to not follow Raoult's law, especially when you're dealing with solutes. The solutes typically don't follow Raoult's law. They follow what's called Henry's law. The concentration, Henry's law basically says that the concentration of a volatile solute in a liquid mixture is directly proportional to its partial pressure in the vapor. Okay? So now the proportionality constant depends on what units you're using for your pressure and your concentration. What we're saying here is this. Here's a mixture. Okay, so let's say it is liquid A plus volatile solute B, and then you have B in the vapor and A in the vapor as well. Okay, the partial pressure of let me change this up. Let me fix that up for consistency with what I have written here. Let's just say you have water, okay, just to make things simple. Let's say you have water here and you have some A in water, okay, so, and A happens to be a volatile solute. So you're going to have water vapor here in equilibrium and gaseous A, okay, so you have A gas in equilibrium with A in aqueous solution, okay. The partial pressure of A in the gas phase is directly proportional to its concentration in the liquid phase. So it's directly proportional to its mole fraction, if we want to use mole fraction as our way of expressing concentration. Okay, so in other words, you can say then that P sub A over XA is equal to a constant. Okay? Or you can say X sub A over P sub A is equal to a constant. Anytime two things are directly proportional, the ratio of those two things is a constant. Okay, so whatever the constant is, it depends on how you write your equation. And so we generally refer to that constant as K sub H. Okay, this is K sub H. All right, and the unit for K sub H depends on how you express your proportionality. What do you put in your numerator? What do you put in your denominator? And so when you look these constants up from handbooks, make sure you check the units, because the units will tell you how the proportionality relationship is expressed. Okay? So if your K sub H, your constant is in pressure, that means this is the relationship. You have pressure over mole fraction. Mole fraction is unitless. What would be the unit for K sub H if this is how the concentration and pressure are expressed? Let's say concentration of A over partial pressure of A is equal to Henry's law constant, K sub H. What would be the unit for K sub H here? What's the unit for A? Concentration of A. Moles per liter, right? What's the unit for pressure? Atmosphere or torr or whatever. So your case, if you see a Henry's law constant given as moles per liter per atmosphere or moles per liter per torr, okay, that means this is the expression that is used, that constant is being used for. Okay. What if your unit is, what would be your unit if your expression is pressure over molality? If your Henry's law constant is given as the ratio of pressure to molality, what's the unit for pressure? Torr or atmosphere, right? What would be unit for molality? Moles per kilogram, right? So that's one possible unit. So your Henry's law constant would be given in atmosphere per mole times kilogram. Okay? So just be aware of that when you're doing Henry's law problems. Keep track of the units because it tells you what the equation is that's being used. Okay? So anyway, What this is saying is the higher the partial pressure, so the more concentrated the solute is in the gas phase, that means the higher its concentration. So you have more, the higher the partial pressure in the gas phase, the higher the concentration in the solution. That means the more soluble it is in your solution. Okay. So let's look at an example. If you open a bottle of soda, carbon dioxide comes out of solution. The bubbles you see, that's CO2, carbon dioxide coming out. That's why it's called carbonated, right? This suggests that the pressure of CO2 in the sealed bottle is higher or lower than the partial pressure of CO2 in the atmosphere. In the sealed bottle versus when it's open to the atmosphere. Higher or lower? So the answer is higher. Good. Okay. Pressure is directly proportional to the concentration. The fact that the carbon dioxide bubbled out means what? When you open it up, you've lowered the solubility. So that's why it comes out. Otherwise, it will not bubble out if the solubility has increased, right? Okay. Estimate the molar concentration of oxygen in water if it is saturated with oxygen. So if your water can hold the most oxygen that it can hold, what would be its concentration? If your Henry's law constant for oxygen in water is 1.3 times 10 to the negative 3 moles per liter per atmosphere, and air is about 21% oxygen. Okay, so the air you breathe is mole fraction of O2 in the air is, let's call that YO2, is equal to 0.21. So what's the partial pressure of O2 in the atmosphere? If air is 21% oxygen, what's the partial pressure of oxygen in the air? What's the pressure of the air typically? 1 atmosphere. So what's 21% of 1 atmosphere? 0.21 atmosphere, right? So you say mole fraction of O2 is PO2 over P total. Okay? And you're given that the mole fraction is 21%, or mole percent is 21%, so your mole fraction is 0.21, and your P total is 1 atmosphere. So partial pressure of oxygen in the atmosphere is mole fraction of O2 times the atmospheric pressure. So it's going to be 0.21 times 1 atmosphere. So it's going to be 0.21 atmosphere. Okay. Now let's look at our Henry's law constant here. Look at the unit for Henry's law constant. Molarity over atmosphere. So what's our equation for Henry's law? What goes in the numerator? Something that has molarity, right? So concentration of O2 goes in the numerator. What goes in the denominator? Pressure quantity. So partial pressure of O2 must be in your denominator. So that's equal to 1.3 times 10 to the negative 3 molarity per atmosphere. That's your case of H. So can I solve for concentration of O2 now? Concentration of O2 is equal to K sub H times, this is K sub H, right? Times the pressure of O2, partial pressure of O2. So that's 1.3 times 10 to the negative third moles per liter per atmosphere times the partial pressure of O2 is 0.21 atmosphere. Okay? So what is that number? .3 times 0.21 is 0.273 times 10 to the negative 3 equals 2.7 times 10 to the negative 4. Okay. moles per liter. Notice that's a very small number, okay? So in cases like this, typically when you look for solubilities of oxygen in water, you would probably encounter this in your biology classes. You've heard of dissolved oxygen. Okay, they're given in ppms. So let's convert this to ppm. Anytime you've got very low concentrations, it's better to express them as ppm. So this is going to be 2.7 times 10 to the negative 4 moles of O2 per liter of solution, right? So how do I convert moles to grams? What's the molar mass of O2? 32 grams, 32.00 grams per mole. So moles cancel out. And that would give me, and then ppm is what? It's milligram per kilogram, right? Or milligram per liter if it's very low. So let's change this to milligrams. So 1,000 milligrams per gram. So that gives me how much? 2.7 times 10 to the negative 4 times 32 times 1,000. That's 8.7 ppm. Okay, 8.7. So that is 8.7 milligrams per liter. Okay? Milligram per liter is ppm, provided the number that goes with it is a small number. When you're dealing with very dilute solutions, a liter of aqueous solution is essentially equivalent to a kilogram of solution, because water has a density of 1 kilogram per liter. Okay? Now, so this is equal to ppm only when you're dealing with very dilute solutions. And that's usually the cases where you use ppm anyway, when you're dealing with very dilute solutions. And for as long as you're dealing with aqueous solutions, then milligrams per liter is essentially the same thing as milligrams per kilogram, or ppm. So 8.7 ppm is as much oxygen you can put in your water to dissolve it in the water. Here's another example. Suppose a scuba diver goes down to a depth of 100 feet. Okay, so here's your ocean. Your scuba diver's down here, 100 feet below. But approximately how much will the concentration of dissolved gases change in his bloodstream? Air pressure at the surface is 1 atmosphere, right? So what happens when you go underwater? You subject yourself to an additional pressure, right? So what's the pressure due to a column of water? Pressure due to a column of liquid is density times acceleration due to gravity times h. Or you can see it's directly proportional to the density. So the more dense the liquid, the higher the pressure due to a column. So you can just compare that to a column of mercury. A column of 1 millimeter of mercury is equivalent to 13.6 millimeters of water. So it's easier to do it that way. Let's calculate the pressure due to a column of water. So first of all, let's see how express this in terms of millimeters. So 100 feet of water. Let's change that to millimeters. How many inches in a foot? 12 inches in 1 foot. And inches to centimeters. 2.54 centimeters is exactly 1 inch. Okay. And a centimeter is 10 millimeters, right? So 10 millimeters for 1 centimeter. So that gives us how much? 100 feet times 12 inches per foot times 2.54 centimeters per inch times 10 millimeters per centimeter. That's 30,480 millimeters of water. Okay? So that's the pressure due to a column of water, 30,480 millimeters of water. So let's change that, 3,480 millimeters of water. Let's look at the equivalent pressure in mercury. 1 millimeter of mercury is 13.6 millimeters of water. Mercury is much heavier than water, 13.6 times heavier. Okay, so that gives us a pressure due to a column of water, 100 feet of water, to be how much? Divide that by 13.6. That's 2,241 millimeters of mercury. Okay. And let's change that to atmospheres. Okay, so before, since we already know the atmospheric pressure. So what's 1 atmosphere? 760 millimeters of mercury. Okay, so millimeters mercury cancels, millimeters water cancel. So that pressure is how much? Divide by 760, 2.95 atmospheres. Okay? That's in addition to the pressure due to the 1 atmosphere above the ocean, right? So what total pressure are you subjecting yourself to when you go 100 feet underwater? About 2.95 plus 1, that's about 4 atmospheres. So if you're subjecting yourself to 4 times more pressure, okay, and so what happens to the solubility of the gases in your bloodstream? It will be 4 times as much. So if you're breathing in that oxygen from your scuba tank, you can get 4 times as much oxygen, 4 times as much nitrogen in your bloodstream underwater. Okay? And what happens if you suddenly rise to the surface? You'll bubble out just like bubbling out of your soda. And that's going to be really painful. Okay? So you need to spend some time decompressing. You don't just suddenly rise up to the surface. So what would be the answer to this one? 4 times. 2.95 plus 1, that's about 3.95 times. Okay? Now, if a solid obeys Raoult's law, then automatically it obeys Henry's law. Why is that? If Raoult's law, remember, says PA is equal to PA star times XA, right? So we can identify PA over XA as just PA star. So that means our Henry's law constant in this case is just the vapor pressure of pure A. Okay? Now, in general, KH, the Henry's law constant, is not necessarily equal to P star A, like I mentioned earlier. For example, acetic acid in water. Okay? In water, your Henry's law constant is 1.3 torr, but pure acetic acid liquid by itself would have a vapor pressure of 15.73 torr. Okay? So, like I said, solutes generally don't follow Raoult's law. Okay, there are some cases that do, and that's what you would call an ideal situation. Now, what would be the vapor pressure of acetic acid in a 1 molar acetic acid solution? So let's say you have a solution of water, of acetic acid in water. Okay, and the concentration is 1 mole per kilogram, 1 molar. What's the partial pressure of acetic acid here? Henry's law, right? You're going to use this Henry's law constant right here. So, but the first thing you need to do is calculate the mole fraction. Okay. So, partial pressure of acetic acid is equal to Henry's law times mole fraction of acetic acid. Since your Henry's law is given as constant is 1.3 torr. So this is 1.3 torr times the mole fraction of acetic acid in your water. So how do you solve for a mole fraction of acetic acid? So you need to change from molality. So 1 mole per kilogram. How do you get mole fraction? Conversion from one unit to another. So let's assume you have 1 kilogram, right? 1 kilogram of solvent, 1 kilogram of water. Okay. So how many moles of acetic acid would you have? If it's 1 mole, 1 mole, right? 1 mole of acetic acid. How many moles of water would you have? If I have a kilogram of water, how many moles is that? 1,000 grams divided by 18.02 grams per mole, right? What's 1,000 divided by 18? 55? 55.15? 55.5 moles. So what's the mole fraction of acetic acid? Moles of acetic acid over moles total, right? Moles of acetic acid is 1. Total moles is 1 plus 55.5. Okay, we're just assuming that number 1 there is exact. So what's 1 over 1 plus 55.5? 1 divided by, 1 divided by, okay, 1 divided by 56.5, 0.0177. So what do you do with that? Plug that in here. Mole fraction of acetic acid is 0.177. Okay, so that will tell you the vapor pressure of acetic acid. Now, acetic acid is what gives you the characteristic smell of vinegar. Acetic acid is vinegar is 5% acetic acid in water. Okay, so that acetic acid in the gas phase, those molecules travel through the air, goes through your nose, and hits the receptors in your nose, inside your nose, which sends nerve signals, electrical signals to your brain, and that's how you smell acetic acid. Okay. All right. How can you express Kh in torr per mole per kilogram? Then you're going to say that would be equal to Kh in a different unit times 1, right? So what would that be? Whatever this number is, right? That's going to be equal to the Kh in moles, in torr per molality. All right, so I think we'll stop there.